Welcome to the lesson that defines Rust. Ownership is what sets Rust apart from almost every other programming language. It's a set of rules the compiler applies to your code to guarantee, at compile time, that memory is managed safely, without a garbage collector, and without the crashes and security holes that plague languages that let you manage memory manually. Let me give you some context. In languages like C and C++, you manually manage memory. You allocate it and you free it. Forget to free, you leak memory. Free something twice, you crash. Access something after it's been freed, you open up a security vulnerability. In languages like Java and Python and JavaScript, a garbage collector handles this for you, but at the cost of unpredictable pauses, runtime overhead, and the loss of fine control over when things happen. Rust does something genuinely new. The compiler tracks who owns what and automatically cleans up at exactly the right time. No runtime cost, no manual freeze, no pauses. If you've heard people say Rust has a steep learning curve, ownership is usually what they mean. But the rules are actually simple. Once they click, you'll see how they enable everything else Rust is known for: fearless concurrency, predictable performance, and code that just works. Let's walk through it carefully. Before we talk about ownership, we need to understand where data lives. Rust cares about the difference between two regions of memory, the stack and the heap. The stack is fast, organized, and structured. It stores values of a known, fixed size at compile time, like an integer, a boolean, a fixed-length array. Every time you call a function, a new frame is pushed onto the stack. Every time a function returns, that frame is popped off. Pushing and popping are essentially instantaneous. The heap is slower, but flexible. It's where you allocate data whose size might change or isn't known until runtime. A string whose contents can grow, a vec that can hold any number of elements, a large object. Heap allocation means asking the operating system for a chunk of memory, which is relatively expensive compared to stack operations. Simple types like integers, floats, and booleans live entirely on the stack. A string or a vec is a hybrid. The actual data lives on the heap, but a small header, typically a pointer, a length, and a capacity, lives on the stack. When you pass a string around, you're moving that three-word header. The heap data stays put. Ownership, as we'll see, is the compiler's way of keeping track of heap data, making sure it's freed exactly once, at exactly the right time, without any human effort and without any runtime cost. Ownership comes down to three rules. Just three. Memorize these, and most of Rust's strangeness will start to make sense. Rule 1. Every value in Rust has exactly one owner, a single variable that is responsible for it. When you write let s equals string from hello, the variable s is the owner of that new string. Rule 2. There can only be one owner at a time. You can pass ownership around from one variable to another, from a function into another function, but only one thing holds it at any given moment. Rule 3. When the owner goes out of scope, the value is automatically dropped. Its memory is freed. The word drop has a specific meaning in Rust, running any cleanup code for the type and returning its memory to the allocator. That's it. No garbage collector polling in the background, no manual free calls scattered through your code, just a single owner cleaning up at a single, predictable moment. This is what people mean when they say Rust has deterministic cleanup. You can look at the code and know exactly when memory is freed, because it's always at the closing brace of the scope where the owner was declared. Because there can only be one owner, assigning a heap allocated value from one variable to another transfers ownership. Rust calls this a move. After the move, the original variable is no longer valid. Try to use it, and the compiler will stop you with a clear error message saying the value was moved. In the example on screen, we create a string s1, then write let s2 equals s1. What looks like a copy is actually a move. Ownership of the underlying heap data transfers from S1 to S2. After that line, S1 is no longer usable. Try to print it, and you'll get a compile error. This might feel surprising if you come from a language where assignment makes a copy by default, like Java or Python. But it's absolutely key to Rust's safety model. Consider what would happen without moves. Both S1 and S2 would point to the same heap data. When S1 goes out of scope, the data would be freed. When S2 goes out of scope, it would try to free the same data again, a double free. That's a classic source of crashes and security bugs in C and C++. In Rust, it simply can't happen because there is never more than one owner at a time. And because moves happen at compile time, they cost nothing at runtime. It's just a compiler rule. Sometimes you do want a true copy, a second independent version of the data. For that, you call .clone on the value. Clone creates a fresh heap allocation and copies every byte of the original into it. Both variables are now fully independent owners of their own data. The important thing about clone is that it's explicit. You can see in the code exactly when a potentially expensive copy happens. Nothing ever gets deep copied implicitly. If you see your code running slower than expected, you can grep for clone and check whether any of them should be borrows instead. For small stack-only types like integers, booleans, and characters, the whole move versus clone distinction would be silly. These values are already the size of a machine word or two, and copying them is effectively free. So Rust skips the move dance for them entirely and simply copies the bits. These types implement a trait called copy. An assignment of them behaves like you'd expect from any other language. The rule of thumb: if it's entirely on the stack, copying is cheap and automatic. If it touches the heap, Rust makes you be explicit about whether you want to move or clone. Moving ownership every time you pass a value to a function would be tedious. Imagine having to give up ownership just to ask how long a string is, only to need the string back afterwards. It would make writing functions painful. So Rust gives you borrowing. You create a reference to a value with an ampersand and hand the reference to a function. The function can read the value through that reference, but doesn't own it. So when the function returns, the value is still valid back in the caller. In the example, we call length with an ampersand s. Inside the length function, the parameter is of type &string, a reference to a string. We read its length through the reference, then return. When the function returns, the reference goes out of scope, but the underlying string is untouched because the function never owned it. By default, references are immutable. You can look, but not change. This is important. You can have as many immutable references at once as you like, across functions, across threads, anywhere. The data isn't going anywhere and nobody can change it underneath them. This property, unlimited sharing, as long as no one modifies, is called aliasing without mutation, and it's one of the cornerstones of Rust's safety story. When you need to modify a value through a reference, use &mut. Mutable references let you change the value in place without taking ownership. In the example, pushWorld is a function that takes an &mut string and appends to it. The caller passes &mut_s, and the function modifies the original in place. But Rust enforces a strict rule that makes this safe. You can have exactly one mutable reference to a value at a time, and you cannot have any immutable references at the same moment. One mutable or many immutable, but never both. This rule is the reason Rust can guarantee the absence of data races. Two threads modifying the same data, two pieces of code seeing different versions of the same object, iterator invalidation when you mutate a collection while iterating, these whole categories of bugs simply can't compile. If you've used other languages, you've probably hit them. Concurrent modification exceptions, observers getting stale values, inconsistent state during iteration, every one of them comes from violating this rule, and Rust catches everyone at compile time. It's a real constraint. It takes practice to structure code that satisfies it. But it's also the foundation on which everything else is built. When we get to concurrency, this rule is what makes multi-threaded Rust feel so much safer than multi-threaded code in other languages. One more guarantee: references in Rust are always valid. Always. The compiler will never let you create a reference that points to data that's already been freed, a so-called dangling pointer. If you try to return a reference to a local variable from a function, the compiler notices that the local is about to go out of scope and rejects the code with an error about returning a reference to temporary data. These checks happen entirely at compile time. They cost nothing at runtime. They catch a whole class of bugs that haunt C-family code, use after free, dangling pointers into freed allocations before your code ever runs. The fix, shown in the example, is usually to return the value itself, not a reference to it. Move the data out, and the caller becomes the new owner. No reference, no problem. When you genuinely do need to return a reference, Rust's lifetime system will guide you. But we'll save lifetimes for their own lesson later in the series. That's ownership. 3 rules, extended with borrowing and enforced by the compiler. It takes some getting used to. Every Rust programmer has spent an afternoon arguing with the borrow checker at some point. But once it clicks, it changes how you think about memory forever. You'll find yourself structuring code differently, avoiding problems before they can happen. In the next lesson, we'll meet structs, the way Rust lets you bundle related data together. See you there.